You've probably heard the rule, never put metal in a microwave. But here's the strange part. A crumpled piece of aluminum foil can erupt into a miniature lightning storm, while a heavy brass or copper block may sit there almost completely silent. Same microwave field, same frequency, totally different result. So what decides whether metal survives or turns into a spark machine? The answer is not just the metal, it is the shape. A microwave oven fills its metal cavity with rapidly oscillating electromagnetic fields. In most household ovens, the frequency is around 2.45 gigahertz, meaning the electric field changes direction about 2.45 billion times every second. When that field hits metal, it pushes the metal's free electrons back and forth. But in a good conductor, the wave does not travel very far inside. The electrons mostly move near the surface, creating surface currents that reflect much of the incoming microwave energy. That is why a smooth, thick block of copper or brass can look surprisingly calm. The microwave field mainly interacts with a very thin outer layer of the metal. The inside is largely shielded, but foil is different. Crumpled aluminum foil is not a smooth conductor. It is a chaotic landscape of points, folds, tears, corners, and tiny air gaps. An electric charge concentrates at sharp geometry. On a smooth surface, charge spreads out. At a sharp point, it crowds into a tiny region. That tiny region can create a much stronger local electric field than the average field inside the microwave. If that field becomes strong enough, it rips electrons away from air molecules. The air breaks down. For a fraction of a second, it becomes plasma. That glowing bridge is the spark. Crumpled foil makes this worse because it creates many small gaps. One fold sits close to another. One sharp edge faces another sharp edge. As the microwave field drives electrons back and forth, nearby surfaces can reach different electric potentials. Eventually, the air between them becomes the weak point. A spark jumps across the gap. And once plasma appears, it absorbs microwave energy very effectively. The arc gets hotter, the metal edge gets damaged, the damaged edge becomes sharper, and sharper edges make more sparks. This is why thin foil can behave like a fuse. A narrow strip or torn corner has very little cross-sectional area. Current forced through that tiny path creates intense localized heating. A thick block, on the other hand, gives electrons a broad, continuous surface to move across. So the difference is not simply aluminum versus brass. It is fragile, jagged, thin metal versus smooth, massive, continuous metal. That is also why a fork is more dangerous than a spoon. The fork has sharp tips. A crumpled gum wrapper is worse than a smooth metal tray. A gold-rimmed plate can be risky because the metallic decoration is thin and discontinuous. But here's the twist. Some microwave packaging deliberately uses metal. Microwave popcorn bags, crisping sleeves, and some frozen food trays use engineered metallic films called susceptors. These layers are designed to absorb microwave energy and convert it into heat, helping food brown or crisp. The difference is control. The metal is thin in a precise way, bonded to a substrate, and designed for a specific heating pattern. Random foil in a random microwave is not engineered. It is unpredictable. So the real rule is not metal always explodes. The real rule is this: metal reflects microwaves, but sharp, thin, broken, or poorly connected metal can concentrate electric fields, overheat, and create arcs. A smooth conductor can behave like a mirror. A crumpled conductor can become a storm cloud. And inside a high-power microwave, the difference between mirror and lightning may be just one sharp edge.